Amid the scorching plains of South Asia where drought has shaped life for hundreds of years, Pakistan set out to challenge one of its harshest natural limits. Engineers began carving a massive irrigation canal, a man-made canal designed to divert the Indus River deep into some of the country's driest regions. But moving a river across the desert means battling unstable soil, extreme heat, and the unforgiving physics of water itself. So how do you engineer water to flow where nature never intended? Why they need to build massive canal? For decades, southwestern Pakistan were defined by water scarcity. Vast plains lay dry and cracked. Rainfall was unpredictable and brief, and extreme heat made agriculture nearly impossible across much of the region. Yet just beyond these parched landscapes flowed the Indus River, one of South Asia's mightiest water systems. While people still have to queue up for every drop of clean water, that contrast sparked a bold national decision to redirect the river inland across arid terrain and into regions long starved of water. The Kochi Canal project, approximately 499 kilometers long, commenced in 2002 with intermittent construction and was substantially completed after more than 20 years with an estimated total investment of over $800 million. The project employed over 10,000 workers and hundreds of modern construction machines working continuously in challenging terrain conditions. Canal construction process. The first steps have been taken. Hundreds of excavators and massive dump trucks began one of the largest digging operations ever undertaken in modern Israel. Every day, around 70,000 tons of sand and soil were removed from the Negev desert along a construction corridor stretching nearly 250 miles. Over 200 engineers, operators, and laborists worked in rotating shifts, enduring daytime temperatures that often exceeded 115 degrees Fahrenheit. The canal was shaped with a wide U profile about 150 feet across at the base and an average depth of 23 feet to allow water to flow naturally without pumps. The longitudinal slope was held within 1 inch per 100 feet, an incredibly tight margin over such distance. Survey crews rechecked elevation with laser leveling instruments every 160 feet to ensure the canal floor stayed perfectly aligned. Most of the excavated sand was reused to build up both sides of the embankments, forming levees 10 to 16 feet high. In hilly terrain, bulldozers cut the layers step by step, while in low-lying areas trucks hauled in stabilized fill material until the grade was reached. In weak soil zones, engineers drilled 16-inch sand piles up to 20-25 feet deep or mixed cement and clay to strengthen the base and prevent subsidence. The construction site stretched for hundreds of miles, dotted with concrete batching plants, mechanical workshops, and field engineer camps. Under the scorching sun and swirling dust, long convoys of trucks and machines moved endlessly, a mechanical river carving the shape of a real one into the heart of the Negev desert. This excavation phase lasted for months. In the Negev desert, the challenge wasn't just the heat and dryness, it was the thirst of the sand itself, capable of absorbing any exposed water within hours. If the canal bed wasn't properly sealed, that's why the lining phase became one of the most critical stages of the entire project. First, the canal bed and slopes were moistened and leveled with a 2-inch layer of fine sand. Then concrete panels about 4 to 5 inches thick were poured in the sections measuring 16 feet long by 10 feet wide, each separated by expansion joints. These joints were filled with hot bituminous sealant to prevent seepage and allow thermal movement. In areas with unstable subsoil, an additional HDPE geomembrane layer was placed beneath the concrete, fixed with steel anchors and covered with a protective sand cushion. Altogether, more than 220 miles of canal were lined with concrete, making it one of the largest waterproofing systems ever built in the Middle East. Along the embankments, engineers planted vetiver grass and desert acacia to stabilize the slopes and minimize sand drift. From above, the canal appears like a shimmering silver ribbon cutting across a sea of gold, a concrete artery waiting to carry its first life-giving water through the desert. A massive canal can't simply be a trench for water, it requires hundreds of auxiliary structures to ensure transportation, flood control, and proper water regulation. At the head of the system, engineers from WAPTA built the head regulator at the Taunsa barrage, where water from the Indus River is diverted into the canal through 9 enormous steel gates. Along the main road, there are more than 900 different engineering components, including reinforced concrete bridges, spillways, siphons, drainage culverts, and aqueducts carrying water across natural streams. Whenever the canal intersects a road or railway, a new bridge is constructed to maintain traffic flow. In sections that cross natural waterways, cross-drainage structures are installed, large conduits that allow the natural flow to pass beneath the artificial canal. In addition, distribution gates are placed every 6 to 9 miles to control water flow into secondary branches. Everything must operate in perfect harmony because a single malfunction, whether at a gate or an aqueduct, could deprive hundreds of hectares of farmland of their water supply. After more than 15 years of construction, the entire canal finally entered the water testing phase. Engineers opened the gates at the Townsend Barrage, letting water from the Indus River flow section by section, gradually increasing the discharge from 500 to 2,000 and then 6,000 cusecs along the route. Technical teams inspected every point, measuring pressure, checking for leaks, monitoring the canal slopes and recording any ground movement. Every deviation was corrected before the system was fully opened. When the first rush of water flowed through the cracked dry canal bed, the regions of Deir Bugti and Jam Magsi erupted in celebration. Locals called it the day the desert came back to life. Wherever the water reached, cheers followed. It wasn't just a flow of water, it was a flow of hope, the fulfillment of a dream generations of farmers had waited their entire lives to witness the moment rail water finally ran across their land. When the first drops of water reached the arid land, everything began to change, not just on the surface but deep within people's lives. Land that once cracked under the burning sun started to come back to life. Farmers who had once left because of drought returned, pitching tents, driving stakes and plowing the first fields of their lives amid the sand and rock. Water from the main channel of the national water carrier was divided through a network of secondary canals, pressure pipes and drip irrigation systems that delivered it directly to each plant, a technology Israel itself invented to save every drop of water as precious as gold. The project began in 1953 and took over 11 years to complete, costing around 420 million Israeli lira, equal to hundreds of millions of dollars at the time. Once operational, the system could transport up to 72,000 cubic meters of water per hour, bringing fresh water from the north all the way down to the Negev. As a result, regions once thought hopeless were revived into thriving agricultural zones. In the early years, tens of thousands of acres of farmland turned green where there was once only dust and sun. Now stood orchards of oranges, vineyards, wheat fields, vegetable farms and rows of date palms heavy with fruit. Seen from satellites, a long green ribbon winds across the golden desert, the green artery of Israel, the artificial lifeline connecting the north and south of the country. The transformation went beyond the fields. Villages were rebuilt, children had schools and high-tech farms rose from the sand. Other water diversion projects. Continuing our journey, let's explore another water supply project in Asia, but this time instead of drawing water from rivers, they're channeling it directly from the sea through a massive system of steel pipelines. Let's discover how Saudi Arabia built its sea-to-land water network to sustain life in the harsh desert. The process begins by drawing seawater directly from the open ocean and channeling it inland, establishing a steady and uninterrupted supply of raw water for the desalination facility. Large intake lines are first positioned offshore, where installation crews carefully align each section before lowering it into place with heavy lift cranes operating from barges or coastal platforms. As the pipeline extends toward the shoreline, individual segments are connected sequentially, forming a continuous conduit designed to operate under constant hydraulic load. Precision alignment is critical at this stage, as even minor deviations can affect long-term performance and flow efficiency. Once assembly is complete, the intake line is reinforced with structural support frames and securely anchored to the seabed. The installation process begins at large staging yards located along the pipeline route. Here, fully manufactured steel pipe sections are grouped by diameter, length, and installation sequence. Engineering teams carry out final visual inspections, checking pipe straightness, coating condition, and identification markings. Proper organization at the staging area is essential to maintain a continuous workflow, minimize delays, and reduce errors when operating in harsh desert conditions. At the same time, survey teams establish the exact pipeline route across the desert using GPS systems, total stations, and terrain data. The alignment is marked directly on the ground with stakes and visible paint. This stage ensures the pipeline follows the most stable and efficient path, avoiding weak soils, shifting sand zones, and areas prone to erosion. For pipelines stretching hundreds of kilometers, accurate routing is critical to long-term structural integrity. Before trenching begins, the construction site must be cleared and leveled to allow heavy machinery to operate smoothly. Temporary access roads are open parallel to the pipeline to accommodate trucks, excavators, welders, and material transport vehicles in the desert. Site preparation also includes dust control and sand stabilization measures to ensure visibility and worker safety. This is a fundamental step that ensures the smooth operation of the entire construction process. Once the route is finalized, large tract excavators begin digging the trench along the marked alignment. The trench is excavated to precise width and depth, allowing enough space for pipe placement and backfilling. Excavated soil is sorted on site, suitable material is retained for backfill while unsuitable soil is removed. Maintaining consistent trench depth and alignment is essential to prevent pipe deformation or misalignment after installation. In addition, along certain pipeline sections that cross steep and rugged mountain terrain, explosives are used to carve trenches directly into solid rock. Controlled charges are placed and detonated in sequence to fracture the bedrock along the planned alignment. The resulting blasted trench creates enough depth and width to seat the pipeline securely, even in areas where mechanical excavation is impossible. After excavation, the pipe is not placed directly onto the trench floor. A layer of selected material, typically fine sand or screen soil, is spread evenly along the bottom to create a bedding layer. This layer distributes loads uniformly and reduces stress concentrations on the pipe. The bedding is leveled and lightly compacted to achieve the required elevation. In desert terrain with loose, dry soils, this step is crucial for long-term stability. To construct large-diameter pipeline routes, a construction corridor approximately 40 meters wide is prepared in advance, allowing the entire installation process to proceed continuously at an average pace of about 1.5 kilometers per day. Pipe sections measuring around 18 meters in length are selected to reduce the number of field welds while also imposing very high demands on lifting, transportation, and precise alignment throughout construction. At the welding site, a hydraulic internal line-up clamp is positioned inside the pipe joint and expanded with 360-degree gripping shoes to hold the two pipe sections perfectly concentric and actually aligned before and during the route pass. An automated welding operation supported by a workforce of roughly 80 personnel and dozens of specialized machines is deployed and can complete up to 150 welds per day on 42-inch diameter pipes. Once welding is finished, every joint undergoes automated ultrasonic inspection to ensure there are no internal defects. The field joint coating crew then performs abrasive blasting to clean the surface and applies a multi-component liquid epoxy coating, forming a durable, fully sealed protective layer. Before the pipes are lowered into the trench and backfilled, the assembled pipes are lowered into the trench using side crane tractors, specialized tracked vehicles designed for constructing large diameter pipelines. Multiple side booms operate in sequence along the pipeline, each lifting a section of the pipe string using padded slings and steel cables to protect the coating. The pipe string is raised evenly and held suspended above the ground as the machines move slowly along the trench. Precise coordination between operators is essential to prevent twisting, bending, or contact with trench walls. When aligned correctly, the pipe is lowered gradually, centimeter by centimeter, until it rests at the center of the trench on the prepared bedding. Throughout this process, surveyors continuously monitor pipe elevation, straightness, and natural curvature to ensure no residual stress is introduced. This method allows fast, controlled, and highly accurate placement, making it ideal for long, straight pipeline routes across flat desert terrain. After the pipe is positioned, the trench is backfilled in multiple layers. The initial layer consists of fine material to protect the pipe coating, followed by the previously excavated soil. Each layer is mechanically compacted to achieve the required density, minimizing future settlement. In desert conditions where soil structure can be affected by wind and temperature extremes, proper compaction is critical to pipeline longevity. But where does this pipeline get its water from? They turn to a nearly inexhaustible source: seawater. However, seawater contains about 3.5% salt, too salty to drink or use for irrigation. That's why desalination technology was developed, giving Saudi Arabia a nearly unlimited supply of usable water. The pipeline carries water from giant desalination plants located next to the Red Sea. Each day, such a plant can convert 7 million liters of seawater into drinking water, consuming a huge amount of energy. After being desalinated, the water is delivered to residential areas through a modern pipeline network to serve the people of Saudi Arabia. However, the cost is extremely high, around $5 per cubic meter of water, something that in the United States may cost only a few tens of cents.